Okay, hello everybody. What we're going to do here is power through some magnetism notes and get up through slide number 25, which gets us all the way up to which gets us up to magnetic fields. Some of the stuff, most of the stuff is going to be reviewed from last year. I don't think I need to spend too much time on it, so I'm going to go through some of these early slides at least and go pretty quickly. There's a lot of three-dimensional stuff going on here, which is really easy for me to show you when I'm standing in front of you, and not so easy when you're looking at a two-dimensional screen. So I'm going to do my best and try and kind of describe things to you. I'm going to try and find some good examples, maybe even take a few videos myself and figure out the best way to kind of show all these things. So beginning here with our basics, magnetism, we're not going to be talking about positives and negatives as our poles anymore. It's going to be north and south. No monopole, so I can't have just a north or just a south like I can have just positive or just negative. Now I can zoom into one end of a magnet, so that's all I see, and so I have a big north on one side of my picture or something like that, but there's always going to be a pair. There's always going to be a south with a north. Now, all of our magnetism is caused by charge motion. We know it's the electrons that do all of the moving. We still talk about positive charge flow when it comes to current and all that, but it's all based on our negatives. I can have straight line motion of charge like in a wire, or I can also look at the rotation of my individual electrons. So for those of you that have had high levels of chemistry and you've got your up arrows and your down arrows and your orbitals and all that kind of stuff, I'm a little bit rusty on all of my chemistry terms and my pictures, but what we were talking about is the actual spin of the electron, and any motion will cause magnetic effects. Magnetism is quite simply the strangest thing in all of physics that we look at in this class, because none of it makes any sense. Everything happens in weird angles, and it's completely bizarre. So right here, charge motion. If you don't have a charge that's moving, there is no magnetic effects. As soon as it moves, twists, rotates, anything, all of a sudden a magnetic field is there, and then things start to happen. It's crazy. Usually we have random motion. For every up moving electron, you got a down. For every clockwise, you got a counterclockwise, and basically everything just cancels out. These three materials, iron, nickel, and cobalt, are able to get uncanceled electron spin. So we can get all their electrons spinning the same way, and they behave like a magnet. Any permanent magnet that you have, like to play with, it's got one of these types of materials in there. We do have the ability to turn things into magnets using charges and currents, and we can make electromagnets, but that's not what we're talking about. These are naturally occurring magnetic materials. The reason everybody seems to think that all metal is magnetic is simply because we make so much stuff out of iron in the form of steel. That's why scissors and staplers and hole punches and car hoods and table desks, the legs of your desk, all those things, it's why they attract a magnet, because they're all made out of steel, which has iron as its primary ingredient. Now, when you have a spinning electron, we call that a domain. A domain is a group of electrons arranged north and south. And basically what we do is when you have an electron spinning a particular way, it behaves just like a teeny tiny little compass needle. So when you have a compass needle is just a small little magnet. So when you have a big magnet, it's simply made up of a bunch of teeny tiny little magnets. Just thinking off the top of my head, if you saw the Wreck-It Ralph movie where the giant Ralph at the end was made of a bunch of little Ralphs, I guess you could look at it that way. But basically, any big magnet is simply made up of all of the little teeny tiny magnets inside, all lining up. And just like with electricity, the closer something is, the more, or the stronger the effect is going to be. So if I have every single possible mini magnet inside an object, all oriented with north on the right, north on the right, north on the right, then the right-hand side of my piece of metal is going to have a stronger north effect then it's going to have a south effect. And so I end up with the north on one side, and if my norths are all pointing to the right, by default, all my souths have to point to the left. And because of that, I end up with always having a dipole, no monopoles. I can't separate the north from the south. Continuing on down here, here is a picture. So green is my permanent magnet. This is my chunk of iron. As soon as I place it on here, all my little compass needles rotate around, and I have north up, north up, north up, which means I get a north here and a south here. All I have to do is take this and rotate it around 180 degrees, and this big green magnet is going to overpower those little domains, and it's going to realign them. So our polarization is by alignment, not shifting of charges like electricity. It's alignment. Again, it's going to be caused by an external field, just like our electric polarization. And I'm going to say that it's long lasting. You have to hit it or heat it, jar it around, make these things get rattled out of place. That's how you're going to unalign things. So it's much longer lasting than electricity. Electricity, you take away the external field and all the charges go back to where they were. Not the case. So you can take a nail, set on a magnet, leave it there for a long time, take that nail off, and you'll be able to pick up paper clips, which is exactly what we would have been doing if we were in class. Electric polarization, as you can see, it's a shifting of charges. I can snap it in two, or I can do some grounding, and I can end up with a monopole, one big positive, one big negative. Now, I still have some external field. The charges shift, I get opposite ends, and I could get monopoles. Now, undoing this is easy. Ground it, and you're done. Whether you ground each one separately or touch them together to share their charge, grounding, and you're done. When it comes to magnetic polarization, here's all my little domains. Bring in a north end. All these little norths repel away. Opposites attract, likes repel. Now, if I were to snap this thing in two and separate them, what do I have? I still have two domains aligned with north on the left and south on the right. So take a magnet, break it in two, you get two little magnets. I still have an external source. My field caused it. Instead of charges shifting, we have domains aligning. I get opposite ends just like I did before, but there is no monopole because they are aligned. They are not shifted. And it's difficult to undo. You have to literally get these things to no longer point together. And once you get them pointing together, they kind of help each other stay in line. Looking at this one right here, I have a south here. It's going to pull on this north. This north is going to pull on this south. So once you get them aligned, they do a good job of kind of keeping each other in line, so to speak. Hit it or heat it is how you would get those domains to no longer stay aligned. Earth facts, real quick. We actually have a magnetic. This seems to be a little bit out of order, actually. Let's skip forward here. Here we go. Magnetic field, capital B with my little vector arrow. So we got G, E, and B, gravitational, electric, and magnetic fields now. Magnetic field lines, just like what would a positive do, we have to have a definition. The definition is, where would a north needle point? I know opposites attract, likes repel, so where would my north point? It'd point away from another north. It'd point towards a south. And what's unique about a magnetic field line, look at my picture here, inside this big green magnet is going to be a bunch of little magnets. And all these little magnets are north pointing to the right, south pointing to the left. So if you were to hypothesize, say, what if I took a magnet or a compass and placed it inside? It would align with every other domain, and what we get is field lines is where the north points, comes out of the north into the south, and this right here is the important one. We get complete closed loops that literally go right through the magnet. Our electric fields, we had field lines dead ending at a negative. We had field lines starting at a positive. Not the case here. They are complete closed loops. Every single magnetic field line you see is part of a bigger closed loop. Here I can see the whole thing. Obviously, if I were to just zoom in on that right there, I would only see just one south end. Know that that line represents a full, complete loop. Trying to draw this two-dimensionally is tough, so I've got some pictures that I have stolen off the internet so you can see a real good three-dimensional vision there. Coming down here, so here's the magnetic field around the Earth. I have a fake apple in my class where I've taken a Sharpie and drawn lines going around it. So if this were an apple and I drew these red lines going around it, I like that because it gives you a good three-dimensional picture. You got to have the three-dimensional picture when you're doing these magnetic field things. So this right here is our course. If I'm standing on the surface of the Earth and my north needle points to the north, for a physics student, that shouldn't make any sense anymore. Say, wait, why does my north point to north? Shouldn't they repel? You're absolutely right. What we have is a magnetic south actually located up here. And it has to do with the history of things. We defined north as a human race long ago, and then we found these little pieces of rock that would align with north. So we said north points to north, makes sense. And then we eventually figured out the physics, and we realized, whoops, opposites attract. So technically you have a magnetic south where our geographic north is. And it's caused by this iron core in the center. The iron core doesn't go all the way up to our pole, which means that your field actually goes down through the crust of the Earth. If we're right about here at 42 degrees latitude, that right there is the direction of your magnetic field. It's going into. So we are so used to dealing with just the north, south, east, west direction. There's actually a vertical direction as well. That's called the dip or the inclination. So if I go to our Earth slides, geo north pole is our magnetic south pole. Declination. Magnetic declination is really only necessary for navigation. The geographic location of your North Pole is the axis around which the Earth spins. That is not where your compass needle is directed. It's actually off a bit because our Earth is asymmetric slightly. The inclination or the dip is the vertical component. And evidence has shown we have found little domains in the sea floor of moving plates that show that the domains have been reversed every 10 to 25,000 years. We are at about 10,000 years now, which means that we could possibly see a reversal of the poles again. Probably not likely, but who knows? But we do have scientific evidence that suggests those poles have been reversing multiple times. It has to do with the core samples they've taken from the Atlantic Ocean. You've got the mid-Atlantic ridge kind of slowly separating, so you basically different locations on the seafloor correspond to different time periods in Earth's history. Pardon me. Now, when it comes to a magnetic field around a current carrying wire, well, if I have all the charges in my wire moving in a straight line, they're all doing the same thing. They're not going to cancel out. We end up with a magnetic field. This is different from domains and naturally occurring magnets. As I take a look, and we would see this in class, we demonstrate it with the wire and with the compass, but what we get is we get these circles, a circular shape around the wire. So if I scroll down just a little bit, an X is a vector arrow that points into the page, away from you. I said that's the feathers of the arrow leaving you if you're using a bow and arrow. Here, the arrow is coming towards you. You see the dot, the dot of the arrowhead coming towards you. A dot means out, and X means in. It's just a vector arrow. So we've got up, down, left, right arrows, and we've got in and out arrows. And if you were to take your right hand, sorry lefty folks, it's got to be your right hand. Actually, you lefty folks have an advantage because you can continue to hold on to your pencil with your left hand, while us right-handed folks have to put our pencil down to do the first right-hand rule. First right-hand rule uses finger curl. Take your thumb, have it point in the direction of the current. Your finger curl is going to match up with the curl of or the direction of your magnetic field. So we have our first right-hand rule. Know what the shape looks like and simply use your finger curl for the direction. You know you're going to get a circle. The question is clockwise or counterclockwise. Use your right hand, you'll get an answer. If we come down a little bit, what happens if I am looking at the wire from the side? I still know that I'm going to get, let's add it in here, I still know that I'm going to get magnetic field lines that look like this, and this, and this. There's my attempt at a three-dimensional picture. The question is, which way are those loops? Which way are they pointing? So my X shows that my loop goes in here, goes around the back, and then comes out over on this side. And if you took your right hand up to the computer screen right now, your fingers, your right hand fingers will be going into the screen when they're on the right hand side of the line. Rotate your wrist a little bit, keep that thumb pointing to the top of the screen, and now your fingertips are going to point out of the screen, hence the dots and the X's. I need to have complete closed loops, which is why I have 3 dots to match up with my 3 X's. If I had a 2 and a 3, that means one of those lines is not coming in or out, and that doesn't show me a complete closed loop. You only get good at that with practice. I'll offer up some first-year physics practice worksheets so you can double check on those if you'd like. Here's some more pictures. So again, these I just stole because they are much better three-dimensional pictures than I could ever hope to draw. So we've got our concentric circles. Now I get multiple circles. I have more than just, a magnetic field in this one location. The magnetic field continues to be present as I work my way out from a wire. We would probably expect the strength to be reduced as we get further and further away. Here's a good visual of the right hand rule. So there's the thumb of the person pointing this way, and their finger curl is going into the board on the top, and it would be coming out on the bottom. So your current and your finger curl. So coming down here, notice there is no concentration of lines going in or out of anything. There is no north and a south. A north is when all your lines go into the same spot and concentrated, and they come out of a spot. Now don't confuse that with this picture. Say, wait, don't all the lines go into the board here? When I say in, I mean they all come together and condense, like this picture right here. They're all coming together, condensing down into one single spot. Continuing down here for the Earth, they're all coming into one single spot. That's different than having a line of charge and having an arrow in on the top and an out on the bottom. So there again are some pictures there. So pardon me. So this one I like because it shows you three-dimensional picture and how it would look on a piece of paper, perhaps. Same thing here. So I've got my picture here. I can see where the dots and the X's are going to go based on this three-dimensional picture. So thank you, Google, for allowing me to see your images and to steal them. More pictures of magnetic field arrows being drawn around different things. Here I start to take my wire and I start to bend it. So if I bend it a little bit, I still get X's on the right, dots on the left, a little bit more, a little bit more. Pretty soon when I bend it all the way around, I have now concentrated, there's that word again, concentrated. I have concentrated all these X's on the inside. So I've got, if you can kind of visualize this, I've got my magnetic field lines are going in and out. But now I have up, down, left, and right locations for these little dots. So top to the right to the bottom, I got all those lines all coming in and condensing down into one spot. My field inside is stronger because my lines are all concentrated, just like electric field lines. The closer they are, the stronger it is. They all enter one spot, so that's actually going to produce for me a south. So a wire, the magnetic field caused by a wire, could have a north and a south. I just have to take that straight wire and bend it into a circle. I still don't have any domains, and what I do is I get a north and a south, and here is my picture. So look at each little segment. There's one segment of wire right there. Let's go with blue right here. There's one segment of wire, and that's the red field that goes around that wire. And then here's the field around the different part, and a different part, and a different part, because I keep on changing direction. And if you notice, every one of these has an arrow going in, arrows going in, in. All these things condense together, and I get an in and then an out. If I were to take this thing and rotate it from the side, it looks like this. And that looks just like a magnet. Instead of a coil, I could put a magnet here, north, south, complete loops going around. And we now have a north and a south. We've concentrated all those lines on the inside. So if I want, I can actually design an electromagnet, a magnet that I can turn off and turn on. I need a battery. I need a wire that's twisted into coils. And if I want, I can put a chunk of metal in there. Iron or nickel would be preferred. Cobalt's kind of hard to get big chunks of cobalt. Iron or nickel would be preferred because they have domains. So I can turn on the blue current. I can produce this magnetic field, and that magnetic field in turn will align the domains, and I get added strength. I don't need to have the core though. All I need is the battery, the wire, and coil. So come down here. Again, another picture that I have borrowed, and so I can see all those field lines going through there. No core, I still get those arrows. Imagine placing a nail in there and all those domains aligning and giving me extra strength. So I need current, I need a coiled wire because that's going to concentrate those field lines to give me south pointing in, north pointing out. The core is optional. It's good for structure. If I have something, a big chunk of metal, I can wrap my wire around it very easily, and I also have those domains. Now, we start talking about forces. So if I have a magnetic field, any moving charge has a magnetic field, which means it will experience a force from some external magnetic field. When you look at gravity and electricity, what you're looking at is the interaction between two separate fields. My gravitational field and the Earth's gravitational field affect each other, and the way they react is causing attraction. Same thing with electric fields. We don't usually talk about the field interaction, and we're not going to here. You just have to understand only something that has magnetic qualities can be affected by a magnetic field. So a charge that's not moving has no magnetic qualities, will not be affected. Only once it starts to move will it be affected. So what we're looking at here is we're looking at singular charges moving. So our force felt is going to depend on the field that we're in. More field, we're going to feel more force. The charge Q and the velocity v. Charge Q is the amount of charge I have. The more charge I have, the more magnetic effects I'm going to have, and the faster it moves. I don't have any magnetic effects until I move. So the faster I move, the more my effects are going to be noticed. So these three things go together, and that right there represents our relationship. Now this is where magnetism gains its weirdness superiority over everything else we've done so far. It's a cross product. What does that mean? It means that the velocity, the motion, has to be perpendicular to the magnetic field. So if I have a magnetic field pointing in one direction and I shoot a particle, if I shoot a particle to the left, I'll get a different reaction than if I shot it up, or if I shot it, north, south, east, or west, up, down. I get different effects just in the direction that I shoot them. So I have to have them perpendicular. So if I have a magnetic field in my physics classroom that points to the north, if I take a particle and shoot it to the north, absolutely no force is felt. Take that same particle and simply do a 90-degree turn and shoot it to the east. All of a sudden, it experiences a force. Shoot it up, it experiences a force. Shoot it to the south, no perpendicularity, no force. It's weird. And what we have right here is a reminder of what the cross product says. Thumb cross fingers equals palm. V cross B. You have to keep that order intact to figure out the direction of the force. And again, you only get good at this with practice. So this is a right-hand rule, so right-handed folks got to put the pencil down. All of our rules are based on positive charge still. If I shoot a particle and I see that a positive particle gets deflected up, what would a negative particle do? It'd get deflected the opposite direction. So I use positive charge, right-hand rule, figure out what a positive would do, and if it's a negative, my answer is just the other direction. Mr. Laura, my left hand is opposite from my right hand. Can I use the left hand rule for this kind of stuff. Yes, but I wouldn't suggest it because that can get really confusing. Which hand am I using? I forget, and the next thing you know, you're using your left hand when you should be using the right hand, vice versa. I'm not a fan of that. Right hand rule for life for me, and when I get my answer, I look at the question. Am I dealing with a positive or a negative? Oh, I'm dealing with a negative? Then the answer that I had as up, opposite of that is down. The answer is down. Now, I come down here. When my particle gets shot into the presence of this field, if all other fields, electric and gravitational fields, are irrelevant because they're small, if we look at just the magnetic force caused by the magnetic field, well, take a look at this picture right here. My velocity is to the right, my field is going in, so literally take your right hand right now and give it a try. Make that thumb. I call this third right hand rule, we don't curl our fingers. I call it the stop hand. If you put your hand up to tell someone to stop, look what your hand does. Your thumb goes out to the side. Since it's your right hand, your thumb is pointing off to the left, your fingers are pointing straight into the air, and your palm is facing away from your face if you're to tell someone to stop. So take that thumb. Thumb is your V, so take your thumb and send it to the right-hand side of your screen. The X's here and here and here represent the magnetic field. Fingers field. Point your fingers into the screen. Make your thumb point to the right of the screen, and by default, your palm is going to the top of your screen. I call the palm the push. Push is a force. Fingers field, palm push. So I get a blue force pushing on my black charge. You'll notice they're perpendicular. We were called circular motion. That doesn't cause a speed change, it causes a direction change. And as soon as my direction changes, my cross product's going to change a little bit. So now take your fingers, keep them pointed into the screen, rotate that thumb up a little bit, pointing in this direction here, and your palm now faces this way. What you get is uniform circular motion caused by a magnetic field. Could I bring in other fields to negate that? Yes, I could have an electric or a gravitational field, but if it's just a magnetic field, we get uniform circular motion. If I have a little bit of speed, a little bit of velocity that's going in or out of the board, then I get a circle that travels. Imagine a circle spiraling towards your face here as it's coming out of the screen, spiraling. We call that a helix. So that's what happens when we have our magnetic field acting on our charged particles. A cross product produces a sine function as long as it is tail to tail. So scrolling back up, there is our equation. Now, I don't think I noted on here the unit for a magnetic field is a Tesla. An electric field was a Newton per Coulomb, and a Newton per Coulomb. Our electric fields were usually a lot of newtons per coulomb. You'd have numbers in the thousands. For your magnetic field, you're talking smaller numbers. You're talking in the tens or so. So much smaller, typically, when you're doing your work. So if I scroll back down here, so just some pictures there reminding you, you can take your velocity arrow and show it as components and multiply the perpendiculars. You can take your field and break it up and multiply the perpendiculars. You'll get the same answer either way. So just a reminder on that. Unit, there it is, the Tesla. So Newton per amp meter is the Tesla. An amp is current. Meter is length. So if I take QV and change into I and L, what we get here is the force felt by a current carrying wire. So instead of a single particle being moved, you now have a line of charge moving along. So why isn't it just IL cross B? Well, our wire can be twisted and bent so that there are different directions. Your particle to the top here, your individual particle has one single velocity, one single direction at one single moment. If it changes direction, no big deal. It still has only one direction at that moment. Well, my current is a bunch of charges all moving along together. So I could have one part of my current going up, the other going right, because maybe it's bent into a coil. So it's technically an integration. We find the small amount of force felt by a small amount of wire, and then we add them all together. So those are our two equations. Make sure we're using amps, meters, Tesla. Make sure we are using coulombs, meters per second, and Tesla. If you're using any other unit, you must do conversions if you're expecting to get Newton as your answer, as your unit. So any moving charge, it's the same slide, so sorry about that. Moving on. So we got a third right-hand rule. Thumb is the direction of the motion, so it's either my velocity or the direction of my current, using positive as our default. Even if you have a negative, go with a positive. Fingers field, palm push, positive test charge. So solving, you can do tail to tail, and you can use a sine function. You can use I, J, and K. If you're given that, you can do the distributive property that we did a long time ago when we first got into our cross product, and then you can also use perpendicular components and the third right-hand rule. So you have those examples. So here what I have is a red wire producing a red force. So the red dots, the red X's correspond to the field produced by the red arrow. You can double check with your first right-hand rule. There's one right there. First right-hand rule, third right-hand rule. You got to know the difference between them. First right-hand rule is for the field around the wire. Third right-hand rule is for the felt force. So my red arrow here, and those are the field lines caused by my red current, and then here's my blue current and the field lines caused. So the red arrow will be pushed by the blue dots. The blue arrow will be pushed by the red X's. And go through and do your third right-hand rule. This one right here would be your thumb going to the right. The blue external field dots means your fingers are coming towards your face, and your palm should be pointing down the page. Third law says I should get a force going up on the blue. Double check. Thumb to the right. Fingers going in. Palm points up. Yes, I get two forces that produce an attraction. So if you have two forces, two wires carrying current in the same direction, they'll actually pull in on each other. Let's see. And if I had wires going the opposite direction, they would repel. A nice demonstration in class that we can't do. So here's another picture, I think a better picture of this object moving along in a circle because of the presence of a magnetic field. So mv squared over r is uniform circular motion. QVB is our magnetic force equation. So these two things we brought together quite often. A wire is a group of moving charge. They all get pushed up. So if I have a straight line, integrating my I, D, L cross B just produces one single answer. Now, I don't get rotation because this part gets pushed up and this part gets pushed up. So from this one, you'll see a whole chunk of wire literally move in one single direction. A single particle up here, though, will move in a giant circle. So this right here, a velocity selector, if I fire a particle and I shoot it through here, if I have this blue magnetic field, it's going to cause it to curve upward. Well, if I can put in a couple of plates, I can make my particle move downward. And so what I can do is I can pick the perfect combination of magnetic field and electric field, and I have to make sure I have them oriented the right way. I could potentially shoot this particle through so that it experiences balanced forces. The red electric force is independent of velocity. Fast or slow, I get the same red arrow going down. The blue arrow, however, depends on depends on our speed. So if I shoot it really fast, this thing's going to get extra force going up and it's going to crash up here. Shoot it really slow and it crashes down here. Shoot it just one single perfect speed and it goes in a straight line. So what I can do is I can shoot a beam of particles through this little region, and only charges going the perfect speed will come out the other end. Velocity selector allows me to get particles that I know must have a particular speed. And I know they have a particular speed because they made it. If they went too fast, they would have crashed. If they're going too slow, they would have crashed. If I had a negative charge instead, my red arrow points in the other direction, but my blue arrow also points in the other direction. So that's called the velocity selector. So basically those two forces, put them together, and all I need is a ratio of electric field to magnetic field. Once I shoot out the other end, a mass spectrometer is commonly used. Basically, we take away the red electric field, and now this particle travels in a circle. It's going to actually travel in a perfect half circle. As soon as it leaves this region, it's going to crash over here, and we have sensors that'll tell us where it crashed. And what we can do is figure out the diameter and therefore the radius, and we can come over here. We know what the charge is because we charged up our ions. We know what the speed is because of our velocity selector. We know what the magnetic field is because we made it. And we now know what R is. What does that allow us to do? Find the mass of our particle. It's common to use this method for finding the mass of different isotopes, so you can see how many different types of isotopes you have for an element and how often they occur in nature, etc. And the same slide a second time because there's two classes that I had last year. I'm going to try and find a good video for this one. Basically, this magnetic bottle, if you have a magnetic field kind of pointing in a particular direction. So let's say I've got two wires bent into a loop so that I get a red magnetic field between them. Well, if I take these two loops and I move them further and further and further apart, I get this bulge that kind of comes out, but it comes back in. So I get this magnetic field in red that points for the most part to the right. And this is a three-dimensional picture, so what you have to visualize is what happens if I had a particle inside here traveling straight up. Do your third right-hand rule. Thumb goes straight up. Fingertips move or point straight to the right. Your palm is facing into the page, into the computer screen, which means that this particle gets pushed straight sideways, and as soon as it changes its direction, the force changes. And what happens is this particle actually just starts to do this little curlicue. Any side-to-side motion is unaffected by our magnetic field, so it might move one way or another, but basically this thing will stay rotating back and forth in a circle around this red line. Same thing with this one here. And what happens is any ionized gas that I have in here gets stuck. It can't leave. If it starts to leave, it starts to move around in a circle. So you have this invisible magnetic bottle, as we call it, that can literally hold these ionized gases. You don't see anything except the ionized gases staying stuck where they are. So that's how you can contain high energy ions. At the same time, what happens if a particle comes from outside? If a particle comes from outside, it encounters this field and it starts to also make a coil, and it can't get to the inside. That's important when it comes to the Earth. This blue line is a high energy particle shot from the sun. If we got bombarded by these all the time, our satellites would have trouble, us humans would have trouble. Luckily, these particles come in, they encounter the magnetic field that surrounds the Earth, and our magnetic field is not that strong. We encounter that magnetic field, and what do the particles do? They start to move around, and now they get stuck there, literally stuck. Another particle comes from the sun and gets stuck. So what happens? All the radiation that the sun has sent to us is stuck right here in this thing known as the Van Allen radiation belt. The radiation isn't from the Earth causing us protection. It is the result of our magnetic field giving us protection. Only particles that are close to the pole, because if we take a look at our poles, the orientation of our field is going to be up and down instead of kind of in a shell around the Earth. So those are the only particles that enter in, which is why you get the northern lights, because that's where your ionized particles can enter the atmosphere. So when they launched astronauts into the moon, they had to actually account for this. All this radiation. It'd be like sending your astronauts, shooting them through an X-ray machine. And they actually had to think about that. They said, all right, well, there's two. I'll show you some pictures here. There are two Van Allen radiation belts. There's an inner one that's super strong, and the outer one is a bit weaker. So they said, well, what could we do? Well, there's a couple of things we could do, right? We could line the space shuttle with a bunch of lead, but that makes it extra heavy and hard to fire. So instead, what they decided to do, and I'm going to click on this one because this looks like a good one. No, we'll use this one right here. This one right here, if you take a look, we got the inner and the outer belt. This one has a better picture showing you the relative sizes of the belt. So you got the tiny belt here and the big belt. The tiny belt is the one that has all the highest amount of energy. So that's the one that we had to really worry about. So what did they do? The astronauts or the engineers made sure that we launched the astronauts far enough north so that we dodged the inner belt. And then they let the astronauts go flying through the outer, weaker belt. And it was a calculated risk, but they said, well, we'll just make sure you go really fast so you're not, in it too long. So they avoided the strong one, and I'll find the article, a real nice article about that and post that. But they dodged the inner one and just made sure they went really fast through the outer one. And then off to the moon they went, and then when they came back, same thing, they made sure they came in from this northern trajectory. They didn't come straight in at the equator, because that would have had them going right through that belt, because that belt goes all the way around the Earth like it's a donut. So force on a wire. So finishing up here. So something like this. I've got 1, 2, 3 very distinct different sections in the presence of this blue magnetic field. The current and the field are going in the same direction here. They're parallel, no force. This one here, perfectly perpendicular in a straight line, very, very easy, ILB, and you can figure out that it's going to be in the positive j hat, the up direction. What about this one here with the curve? Well, for this one, what you're going to do is you're going to take small little segments. So due to symmetry, I know that I'm going to have 0 in the x, so basically all I have to worry about is the force in the y direction. So in looking at this, because I can see this one has left and right, this one over here has a right and up, a left up and a right up, so the x's cancel out. So all I need to worry about is the y component for every single part, add them together, and I can figure out the force felt by this whole semicircle. So we choose a small little piece, dl, and I use my equation right here. So they are perpendicular because I have an inward facing or inward directed blue magnetic field, and then I've got this segment here which is always going to be perpendicular, and my sine function right here comes to find my y component only. So if I were to kind of if I were to just for a second block this out, so that right there, this is going to be the total force felt by every single segment. But we only want the vertical component, so there's my angle. Sine function gives me my opposite side here, so this is to get the y component. The reason I point that out is we know that a cross product can be used with the sine function. That's not what this is. My cross product is simply multiplication because I have perpendicular. My current pointing up and to the right is perpendicular to a line going straight into the screen. Same here, same here. So this cross product turns into multiplication, and this sine function is to get just the Fy. And so what we do is we're going to go from 0 all the way over to pi, and so you can follow through and you can do the rest of the work there. And that's in our slides. Electric flux is the concentration field that's through an area. We use that with Gauss's law eventually. Magnetic flux, we can do the same thing. Concentration of a magnetic field through a surface. So it's the same equation. Instead of E, it's B. Instead of E, it's B. All the rest is the same. The unit is a Tesla meter squared, known as the Weber, maybe one of the weirdest sounding physics units of all time, the Weber. 5 Webers. That just sounds weird. Now, Gaussian surface, we know how that works for an electric field. When it comes to a magnetic field, Gaussian surfaces are nice because it's always 0. This right here tells us we have a closed 3-dimensional shape. Well, we know that our magnetic field lines are complete loops, so every line that exits and gives us a positive flux has to enter somewhere else and give us an equal amount of negative flux. So because we have no monopoles, we will get 0 for our Gaussian surface every time. Our flux will always be 0 when it comes to a magnetic field. Magnetic dipoles. I'm not going to talk about this. This is just like electric dipoles. It's a subject that we need to know of, but not really used all that often. I've got a real nice three-dimensional diagram to use in class, but I don't have it here. But basically, you've got a coil of wire. So instead of having a positive and a negative, I've got a coil, so I've got an in on one side and an out, and I put that in the presence of a magnetic field. Just like we put an electric dipole in an electric field and watch it rotate, this one here will rotate. So as we go through, we've got our torque, we've got our dipole moment, and we've got a right-hand rule to use, and we've got a way to express all of that. So you can go through the slides there. Dipole energy, so we've got stable versus unstable equilibrium. These two red arrows are causing it to stay where it is. I can balance out these two red forces perfectly, but as soon as I displace them a little bit, this red arrow is going to cause it to rotate around, as will this one. So we've got stable and unstable equilibrium, and ways to calculate that. So not entirely unlike electric fields. And this is where I wanted to stop the Hall effect. This was used to prove that we were wrong all along in talking about positive charge flow. If I have a chunk of metal, this represents one big chunk of metal with current going to the left, one big chunk of metal here with current going to the left. When we have current going to the left, we have always said that's positives traveling to the left. But then we said, well, technically we know that it's actually negatives going to the right, but you get the same effect. Positives going left, negatives going right, gives you the same effect. We just call it positive current. So, okay, shrug our shoulders, no big deal. But if we had positive charge motion, take your right hand. Positive charge is moving to the left. Green external field, so we take this chunk of metal, we pass current through it, and we apply a magnetic field. I'm going to go with an in field. So thumb goes to the left, your finger's going straight to the right, your palm should be pointing down the screen, which means that as these positives move to the left, the green magnetic field is actually going to push them downward, and these positives are still going to move to the left, but they're going to be moving to the left while pushed up against the wall. If I took a voltmeter, I can measure the voltage difference between the top side and the bottom side. And if I use my black lead here and my red lead here, this is high voltage because it's positive, this is low voltage, I'd get a negative reading. Here, current still going to the left, but it's caused by negatives going to the right instead. Okay, everybody, right hand rule, fingertip still going in. Now my thumb is pointing to the right. Your palm points to the top, but it's a negative. So if my palm faces up, a negative gets pushed down. The negatives get pushed down to the bottom as they slowly move. Now if I use my voltmeter, this right here, my black lead is on the low, and my red lead is on the high, which means I get a positive. And so it's actually a very easy way for someone with the right lab material to determine what is it that's actually happening. Is it positives moving left, or is it negatives moving right? And the proof is that it's actually negatives moving to the right. So, like I said, we have proof that we, as a scientific community, were wrong all along in going with a positive conventional current. And yet it sticks. Okay, so a magnetic field from a moving charge will be for the future. So this takes us through slide number 25. I like this picture better because it's got better color. So if you have any questions on this, make sure you let me know. There's an online out there for magnetic force, and the magnetic field will be coming soon enough. So if you have any questions, text me or bring them to our Zoom meetings. So until then, have a nice day.